Мне писали то, что что-то в прошлый раз она как-то плохо записалась, да, я так понимаю?
Да, плохо.
Вот. Интересно, с чем это связано. Получится ли сегодня не пустить этого?
Да, все, теперь просто назад. Ну все, да, здесь ничего не надо больше делать, а? Возвращаюсь в Android. So I want to first of all finish section, I think this is 6.2, with the last statement of the following proposition. So let x and y be, as usual, actually not as usual, we assume that this is quasi-compact. But instead the usual assumption that this is quasi-compact, I want to assume that it's semi-separated. Semi-separated schemes. And also, let's take f, the map from the x to the y. This is quasi-compact, as usual, quasi-separated metal schemes. So then the following diagram is commutative. Notice how my handwriting changed. So I think it's much better now. I think there is some different settings. Yes. Yeah. So then the following diagram is commutative. So, and in this diagram we have the derived category of the Grothendieck category quasi-coherent shapes on X. Then there is a canonical embedding of this category to the d of x. Yeah, d of x. This is my standard notation for the derived category of OX modules with quasi-coherent homology. Now, here we have, since we have map, we have a derived functor, and we have two derived functors, right? So I can compute the derived functor just between the derived categories of quasi-coherent shapes on x and y, right? So since this is Grothendieck category, there is a k-injective resolution for any complex, so I can define the derived functor, but since this is in this setting, this is not the standard setting that we used this derived functor before, I'm going to write QC. And there's kind of the standard derived functor, which is I'm going to denote just R f over star to the d of y.
This is R f over star that's restricted to d of x, yeah?
No. This is I can forget about this part completely. So that's in Grothendieck category.
No, that's, I know, the right part. This is the restriction from
so,
the OX models.
Yeah, this is what we have probably done before, right? The previous lecture, I spent a lot of time on this. You have this functor defined for the OX modules, and then what I show that if you start an object with or complex with quasi-coherent homology, for this functor, you still get something in quasi-coherent homology. So this map is of course just the inclusion, the standard inclusion for variant for scheme one. Okay. That is the statement. So essentially it says that it doesn't matter in which category, well, if you have kind of reasonable assumptions. And I think quasi-compact semi-separated is quite general assumption, because in any applications when you do some real algebraic geometry, you usually have something like quasi-projective scheme, and all these conditions they are definitely satisfied. Okay. So the proof is kind of based on the same idea as the previous proof. I'm going to do some reduction at the end and use the same distinguished triangle, but in the beginning I just want to explain what I actually need to show. So let me take some object E in the derived category of the Q call of X. So let me choose the K-injective resolution. So E map to the I is a K-injective resolution. No, this is in the category mu work. So D Q O of X. So then the simple observation, which is the underived identity. So if I apply I y composition with the F low star applied. Well, I can actually apply to any object, but in this case I need to apply this to this resolution. So then this is the same thing as F low star I sub x applied to. So for the underived case, this is clear, right? Well, because
Well, just
because what you really do. So what this functor is doing, you just apply this functor kind of to each term, and what you do is the I to and take the same complex, but you just consider this complex in a different category. But as a complex, it's the same complex. So I that doesn't do anything, and F is just an application of this underived. It's just an application to kind of termwise in the complex. So that's a simple observation. Now I can write the following composition. So I take u of the y, say the derived functor QC F low star applied to some object E. Well, since I know that the computation of this derived functor, I just need to apply F low star to the resolution, right? So I'll get exactly the left-hand side of the previous identity. So I can as well just write this, that this is equal to the F lower star I sub x applied to this resolution, right? Okay. So then, well, I can claim that the I sub x necessarily preserve the property being injective. But I can do the following. I can take this object I sub x y, and I can choose another K-injective resolution, call this J. But this is of course now in the D of x. So this is K-injective resolution in the D of x. Right? Well, and then what I can do, I just can kind of take this resolution and apply functor F low star to both sides. So then I'll get, if I apply to the left hand side, I'll get exactly F low star of the I sub x of I. This is mapped to the F low star of J. Right, but this F low star of J, I can identify this with derived functor R F low star, right? I'm just taking the argument, which is in this case I sub y, right, sub x,
X
yes, of E, right?
No, why?
Well, because what this functor is doing, well, if I want to compute this thing, I just need to apply F low star to the K-injective resolution of this argument, right? But the K-injective resolution of this argument, right?
Okay, X commutes with homologies, and that's okay.
Yeah. So I can also write this as the I sub x of the I, right? Okay.
Yeah, it's isomorphic. This kind of K-injective resolution.
Okay. So essentially, that's the map, right? So this is the map. So this is kind of, if you look at the beginning of what we've done, this is the composition like this in the square, and then we get the map to this composition. So I want to show that this map is always isomorphism in the category D of y. Okay, so this kind of will be two reductions. So first I want to notice that, let's assume that if, so maybe note, so we can note following simple thing, that if scheme X is affine, right, so then the map F is affine, right? And this follows from the fact, from the assumption that Y is semi-separated. It's just remember that semi-separate means that the intersection of two affine is affine, but if you can have a map from the affine variety, and this map is also affine, since you can kind of check this taken affine in the Y, they look at this pre-image, it's still affine. So there are some details that you need to check, so think about this as some simple exercise of semi-separated maps. Well, but if the map F is affine, right, so then we already know the statement. That was the first statement in this section 6.3. Right, to prove the theorem that the two derived categories coincide, I was using two preliminary statements. One of the statements was this statement for the F being a affine map. So, and the result follows by first proposition of the section. Okay. So now I want to reduce everything to the case when X is affine. To do this, I kind of consider two such squares. So first off, I take, so now let X be general, right? So, and let's take some J, which is just the inclusion of the open, affine open subset U into X. So this J is inclusion So then I have two such diagrams. One diagram will be for the map J, and then there will be kind of the copy of this diagram for the map F. D, Q, O, O, U, I sub U to the D of U. Then there is J lower star. Well, since I know that this on this category, this is affine inclusion, so this is an affine map. Right, so affine inclusion into semi-separated scheme. This is affine, so I don't need to derive this functor. So D Q co of X. Now here there is F lower star, the derived functor. D Q co of Y. And here there is the embedding I sub X. There is an embedding I sub Y, and the functors on this side we suggest the two derived functors for the maps J and F. Well, clearly this is commutative, and
why? So the upper square and the whole square, are commutative, that's why the lower square is commutative.
yeah, yeah.
Mm-hmm.
Well, no. Well, it's not clear that it's commutative. I'm going to show this is commutative. It's clear this thing is commutative, right?
Yeah.
So.
Why did you write J lower star on the left? On the left, right, up, or left, up. Yeah, why isn't J lower star just?
Instead of the derived functor?
Yeah.
Well, because this is affine map.
J.
J.
Yeah.
So U is affine and X is semi-separated, right? So if you take affine subspace here, you intersect with U, you still get something affine. So J is affine map, and you don't need to derive this.
X also is in a separate here.
Yeah, well, and then we have the following. If you take the composition of the RF lower star RJ lower star, well, since we know that the derived functor of the composition is the composition of derived functors, well, if you have kind of all the right assumptions, so composition, right, and this is kind of general property that if you have composition of two maps, that this is true for the derived functors, but there's kind of this little argument hidden here. You need to check to have this formula that the derived functor of some map preserves the property being k-injective, but that's true. It's very easy to verify. And so this is one identity, and the other identity for the derived functors is index QC.
So yeah, why did you write RJ lower star when you go from d of u to d of x? Isn't it also not derived?
Here?
Yeah.
No, this has to be derived because, well, this is just kind of a priori, this is just a functor between OX modules.
Yes.
So how do you know that this is exact if the map is affine? Right, so it can...
RJ lower star like only for
Yeah, so it's kind of exact functor if you restrict to the subcategory, if you restrict to quasi-coherent modules.
Okay.
Yeah, so then the second formula for the for this composition, for this composition. Okay, so now I'm claiming that on the right hand side I don't need to write the derived, I can just take the composition, right? Because if you take this composition, that will be a map from U to the Y, right? And that is affine map, because we already know that we map from the affine scheme to separated scheme is affine. So we don't need to derive the right hand side. Okay, so what I want to say now that just from these two simple observations, we can say that we get the result for objects of a special form. Objects of the form G lower star applied to some object F, where F is an object in the derived category of the Q pole of U. Right? We have objects of this special form. We just look at this diagram and see that this from this the composition of diagram the result follows. Now the last step is to reduce the general situation to this special case. Well, since I know that F is quasi-compact, I can write this X as the union of some UI, so that's a finite union of, so this is covering of X by open affines. It is finite since we have quasi-compact scheme. Okay, so then we prove the result, so general result, by induction order. Of course, the case when n is equal to 1, right, where x is just affine, we already know. So we only need to do the step of the induction. For the step of the induction, let me fix notation, kind of the standard notation in this situation. So let J be the inclusion, open inclusion of the U1, which is U. I'm going to shorten the node just U. So this is the inclusion of the U, which is U1 into X. And the I is the inclusion of the host complement. So X minus U. So this is the inclusion into X. Okay. Now, if I have object E in the derived category of the Q of X, right? Since I know for the schemes of this type, which are quasi-complex semi-separated, the derived category of the Q I can identify with the derived category of Lorentz modules with quasi-coherent homology. Can as well think that this object lives there. And then for this thing, I already know that I have a distinguished triangle. So that's the same distinguished triangle that we used in the previous group. I'll have to check that there's a distinguished triangle as an exercise, but you can notice also one thing that I didn't have time to mention last time, but maybe I mentioned this time. What if you look at the long exact sequence of homology for this triangle?
Don't you do something like there's no homologies that supported on the closed subscheme and
the restriction of the open.
restriction.
And the cohomology for the closed, this is what's called local cohomology. So this is how you can see the theory of local cohomology in the algebraic geometry, which is not affine. It's just an existence of this distinguished triangle. Now this kind of shows how the local cohomology are related to the cohomology of the restricted to the open. This is more or less the same thing up to a shift, right? Because if this is say just a shift, then this cohomology lives only in the degree 0. Right? So then you get the identification between the local cohomology and the restriction to the open subset, which is complement to the closed subset which you use to the compute local cohomology with the shift by 1. Okay, just as the remark that this is something that you've already seen maybe in other courses. Okay, so now the rest is simple, right? If I have this distinguished triangle, so for J lower star, J upper star applied to the E, that's the object of the form that we already know the result, right? So this is J lower star applied to something. So for we know by previous computation, and for the case I lower star R well, since this is the I and this is just will be something which is supported on the closed set x minus u, so this will be supported with on something which is covered by everything starting I equal to 2. Right? So this we know by the induction hypothesis. So, I don't want to write this diagram, but I hope you understand. You have this distinguished triangle, you have map between two functors, you apply one functor to this distinguished triangle, another functor to this distinguished triangle, you have 3 maps. These 2 maps are isomorphism, has the map in the middle, so also isomorphism. That's the end of the proof, and that's the end of the section 6.3. So let me start 6.4. As I don't really have a good title for this, it's kind of the rest of the preliminary knowledge that we need from algebraic geometry. Let me call this relations between derived functors. Well, there are some trivial relations, but here we'll discuss something less trivial. And before we do this, I just need a quick reminder, essentially just a definition. from the category period, so the so-called plumb subcategories. So the definition is the following. So let A be an abelian category. So plumb subcategory is subcategory of abelian category. So full subcategory C in the category A is called plumb. If for any exact sequence with 5 terms, x1, x2, x3, x4, and x5. So that's an exact sequence in the category A with x1, x2, x3, x4, x4, and x5 in C. Term x3 is also in subcategory C. This kind of standard definition that you can find in literature on abelian categories. And I want to formulate maybe as an exercise or as a lemma and leave this as an exercise. This is quite simple. So first part of the lemma is the following. A subcategory C in the A is plumb if and only if C is closed under kernels, co-kernels, and extensions. Which I think it's both part of this lemma is very easy to verify. And the second simple observation that we will need in the later proofs is that a plumb subcategory is closed under direct summons. So leaving this as an exercise, not a very hard one. Okay. So that's just a reminder what plumb category is. And I want to prove the following statement. So maybe I just erase this because the statement is quite long. So proposition. So let P be a property of OS modules and well, I assume that this property is defined for any scheme. And so an example of what I'm talking about is the property like being quasi-coherent, being coherent, being, say, of finite type, etc. So for this property, I want to ask for three requirements, so such that first A subcategory C sub X, which is a subcategory inside the all of its modules, so objects with property P. So this is plump, and this is again for any scheme X. So then I require that for any scheme, again for any X, which is a scheme, and any open covering, UI of X, and OX module, say OX module F, as property P, if and only if, well, we can restrict this F to the UI and require that this also has property P for any index site. So this property that I'm talking about is a local property on the scheme. And the last condition, which is much easier to formulate C, is that Cx is always a subclass in the quasi-coherent modules on X, and that's again for any scheme X. So if now I take F to be an object in the derived category of all its modules, and G, this will be, so this will be in the OX modules, but the cohomology will be in the sets. So this notation is kind of the standard notation, and this is one of the reasons why I need plumb categories, because for the plumb category, so what's this thing? So this is by definition, all the objects, say, might be E in the D of OX, such that the cohomology of the E are in the C sub X for any index, right? So an example such definition will be our definition of the D of X. This will be D of OX Q-core. And you can check, again, maybe this is another exercise on plumb categories, so why we need condition that C of X is plumb, but this again triangulated category. Okay, so we assume this about F and G, and also assume one of the following two hypotheses. So, and one of the following hypothesis is satisfied. So first is that F is perfect, and second is that the F is pseudo-coherent and G is locally bounded below. So under this hypothesis on the property P and two hypotheses on the objects F and G, the conclusion is the following. So then the R home of X between F and G, this is in the D of O X with the index Cx. So in other words, the local x, if you compute between such two objects, so this is again an object in the Cx. And so maybe I write this. So another way to formulate this is that the x I between f and g is in the Cx for any I. Okay, so that's kind of the general statement, and we need the statement, for example, in the situation where the property is just a property being quasi-coherent. So clearly, if the property being quasi-coherent, then these three assumptions A, B, and C are satisfied. It's easy to verify it. So then the claim will be that, well, I think the second one is a little bit more interesting. And the claim is that if the first argument is pseudo-coherent and the second argument, say, again, you take a natural quasi-compact case and then you just can skip this locally bounded, so you can say that this is G is from the D plus. So first argument pseudo-coherent, second argument from the D plus, then the X I again quasi-coherent. So that's a statement, well, that's a property that is not true if the first argument is not pseudo-coherent. If you just take any, say, object from the D minus, from the not necessarily Noetherian scheme, that this is not true. Okay, so but let's prove this in the general form for some property P. So first of all, without loss of generality, I can take X to be affine scheme spec A, right? Since P is the local property, so using P I can go to the to the kind of open affine covering and work with just one of the opens. So let me just fix some notation. So I'm going to call category D with some longer notation that depends on the X, and so that depends on the X and also on the object G. So this will be all objects F in the derived category of OX modules with the property that we want, right? Such that the X, I call this I. Maybe I is not a good index because I have I in the covering, maybe N. So X N F G is in the C sub X or any N. Okay, so first observation that the category D, well, kind of the standard use of notation that I use in this course over and over again. I define the subcategory as a set, meaning that this is the set of objects, and the subcategory is by definition full with these objects. So first observation is that D is, let me write this, full by definition, but which is not by what is not by definition, and this is triangulated subcategory. Right, and this follows from A. Yes, since this is a one subcategory, right? So well, first of all, clearly this is closed under shifts, right? So there's nothing to prove here. But if you want to take a distinguished triangle, for example, you know that the two vertices are in this subcategory, you want to show that the third vertex is in this subcategory. You just write the corresponding log exact sequence of the X, using that this is plumb. You kind of take 5 terms, you have 2 terms will be in the subcategory Cx, so the middle term is also in the Cx. So this is kind of by A and 5 lemma apply to the 5 terms in the log exact sequence of the X. Okay, so one observation, this is full triangulated subcategory. So then another simple observation is that OX is in D, right? Right, because when F is equal to the OX, when I compute, say, X write this R home. This will be a simple formula, easier to understand. So if I look at the R home, OX, sorry, this is what somehow E, but this of course supposed to be G. So G is fixed, and I look at the subcategory of OFs, so that where we have the property that we want to show. So if I plug in this to the second argument G, so how I can simplify this? What is this thing? R home OX.
G?
Yeah, this is just of course G. But by my assumption, G is here, right? So this is in the D sub Cx, D sub Cx of OX. So in other words, if I look at the cohomology of the G, this will be an object in the Cx, right? But the cohomology of this side is exactly the X. So all the X are in the Cx. So that's another simple observation. Okay, so another observation is that the D is thick, which again easily follows from the definition and the fact that Plum subcategory are closed under direct summons. So C sub X is closed. So that's a thick subcategory that contains the structure sheaf. So it contains the perf of X. So that's a subcategory inside D. And this proves part 1. Right? For any perfect, we have the result. Now, for the second part, here in the statement I have locally bounded, but since I can in the proof I work locally, I can assume without loss of generality again. So let me say this implies 1. So for 2, again without loss of generality, I can assume that the G is in the bounded below, so D plus of X, OX. Okay, so then for this G, I have a map. So for the F, right? So F is pseudo-coherent. So let me write what it means. It means that for any integer m, I can write the map alpha from some e to the f, which is m isomorphism, and e is perfect on OX. I can write strictly perfect, but this is just an affine situation. It's the same thing. Now let me fix some notation. So let a be an integer such that G is actually lives in the D greater or equal than A. OX. So equivalently, what I'm just trying to say is that the cohomology, say with index P of the object G are all equal to 0 for any P less than A, right? I know that such A exists since this is in the D plus. I'm just choosing notation for where the complex kind of starts. Right? So it starts at A and all the higher homological degrees. Okay, so then I have the following simple but kind of tedious observation is that if cohomology HP of F is equal to 0 for any P greater or equal than N, then what I need is the observation that there are local home between F and G. This is a cyclic in degrees less or equal than A minus N. Okay. Unfortunately, I need to erase the statement. Okay. So to prove this, well, this is very kind of silly computation with actual complexes, right? I can, so let me say indeed, and this is the proof of this claim. So let G map to the I will be K-injective resolution of the complex G, right? So then I can write this R local home between F and G as just the local home between F and the I. And I also know that if I have this property that the object G is in the G greater or equal than A, then I, the injective resolution, also lives there. Right? Because remember that for the bounded cases, below or above, we have kind of constructed procedure how to produce a resolution, right? Which will be just resolution of injective objects, which is as a corollary K-injective. So by that argument, we know that the K-injective resolution also sits in the same degrees. And then the rest is just you look at the local home in the degree I between F and G, right? So by the definition, this is the product of over the all integers between Fk and Gk plus I. So of course, it kind of sometimes I miss this dot in the formula, but of course, this is kind of the home with a dot. That's the complex, right? So a term in this complex is like this. But now, since I have these assumptions about the
so it should be not for G, but for I.
yeah. Let me change this. This is I. Right? Okay, so I claim, let me just copy the formula and then we check that this works. So that this is actually just a finite product for the K between N on the as the upper bound and the lower bound is A minus I of the homes. Sorry, I wrote product, but this is product of homes, of course. Let me fix this. So this is the product of the local homes, product over all integers. So this is home Fk G K plus I. Right? Well, and this is because the I lives only in the degree I, A, right? And for the Fk, we also know, well, we know that we have this assumption of the cohomology, that there are no cohomology starting at A and then higher, but if this is true for the cohomology, we can do the kind of good truncation and assume the same thing for the complex F itself. And since we have this kind of the vanishing of the Fk's and I with another index, what actually survives is just a final product, so when K is in these boundaries. So we can verify this. I hope that there is no mistake here.
I don't have G in the last form.
No, because I have G in my nose, but this is supposed to be I. And just continue to copy this in whatever way. So if I is less or equal than A minus N, right? So which is equivalent to saying that N is less or equal than A minus I. So then the home I between F and I is equal to 0. This is what we want. So I claim that I'm conclusion this R home is just a home between F and I, and this all the terms in this complex are zero if I have the assumption that the index is less or equal than I minus n. Okay, so that was kind of the silly part of computation with numbers. And finally, I'm going back to the definition of the quasi-coherence, which I wrote in this line, and I look at the distinguished triangle. So that E, F, this is alpha, so I complete this to a distinguished triangle. So the third object is K. And for the K, I know that the homology of the K, HP, are all equal to 0 for any P greater or equal than M. So that's because alpha is an M isomorphism. Okay, so then we have along that sequence. I think you kind of can guess how the proof now works. R home between K and J mapped to the R home between F and J mapped to the R home between E and J. So this is part of the long exact sequence. Well, by what we proved before, kind of just changing my M to the index n that I brought here in the proof, I can claim that this term, this R home, is in the D less or equal than A minus M of X. And this term is in the D sub C of X, Cx of all X. Right? That is because the object E is assumed to be perfect, and for the perfect objects by one, you already know this. So then, well, to convince you, maybe I'll write the 5 terms. So I have text K minus 1 of the E and G, which is mapped to the X with the index K. Arguments are K and G. So then there is X K F G, X K E G, and finally X K plus 1 K and G. So this is the 5 terms from the long exact sequence for kind of homology. Sorry, I was saying that it's not exact sequence, but of course this is just another distinguished triangle which I obtained by applying the functor home into G to this distinguished triangle. Right? So this is a distinguished triangle. There is corresponding long exact sequence of X, which is this one. I wrote 5 terms, and I want to show, well, how I can see by using the Plum condition is that I can choose. Right, so this is pseudo-coherent, so that condition where a fixed integer m works for any m, right? So I can choose m such that k is greater than a minus m. Right, so suppose I kind of fix k, so I want to look at this term, the k is fixed, and for this k, a is also kind of given to me, right? So this is just a property of the g. And then I can take any integer m, so I take any integer m to satisfy this inequality. Right, so then x, k, f, and g is in the cx. Right? But so, but since cx is point. Because in this 5-term sequence, the first 2 terms and the first 2 terms and the last 2 terms are in the CX by this assumption. So they might be vanishing, but CX contains 0. So I want to say that that's the end of the proof.
condition that Cx is plumb. Isn't if we take M to be larger than n plus 1, then R home Kj is lies in the degrees lesser than A minus M. R home Fj lies in the degrees upper. This one.
The last sentence, R home, where?
Fj lies in degrees upper than A minus M. So larger than A minus M. So there's just isomorphism in for R home Ij with well, for X K Fj and X K Ej. So there will be just isomorphism because there's will no.
Yeah, I think this makes sense. And we probably can relax some conditions here in this statement, but I used something, right?
No, I just Cx should be plumb. I just don't understand why you use it in the last statement, because I think the last statement is just true without any condition for Cx, but there we already used plumbness of Cx.
Yeah, we don't. Well, if we modify this statement, right? Well, you can do this, well, because you have this freedom of choosing M, right? But what I want to, well, the main reason I think is that if I want to consider, well, the condition is that I have the D Cx of Ox. I want this to be a triangulated subcategory.
Yeah.
So for this I need pump, and I also need it here. So this is
Yeah, I'm not saying that we don't need this condition. I'm just saying that I don't. Yeah, that's the last statement can be either, but probably it's just the same
so maybe we don't
statement.
have 5 sequences.
Yeah.
Right. Okay, but anyway, so that's just one general statement, and from this statement I want to derive a couple of observations. Say corollary, which I'm not going to prove because I think it's quite easy. So let X be a scheme. Suppose that objects F and G are just two complexes of OX modules. Suppose one, as before, of the following hypothesis. So say A F is perfect on X and B F is pseudo-coherent on X and G is as before, so locally bounded below. Bounded below. So then two observations. If complex G has quasi-coherent cohomology, so lives in the D of X, so then R home F and G also has quasi-coherent cohomology. And the second statement, so how you can derive, for example, 1? Well, you just take the properties P to be quasi-coherent, right? So you check that this satisfies 3 conditions in the previous proposition, which is easy, and then you immediately get 1. So for 2, you take a property of being coherent. So this, I'm just kind of an example of what you can do by the general technique, but it's not what we use later. So if X is locally Noetherian, this is what makes category Cx plumb if the property is being coherent. So G is in the derived category of OX modules with coherent cohomology. So I write this with this index for coherent cohomology. So then the derived local home between F and G is again some complex with coherent cohomology. Or you can formulate this equivalently with the local x being coherent. Okay, so the proof exercise, which is the first part I think I explained. The second part I'm not going to explain because I'm not going to use it. Just one of the details that you can show. Yeah. So there are actually a few more statements of this kind, like this corollary, where everything works. For example, when the first argument in some form is pseudo-coherent, and that's another explanation why you might be interested in pseudo-coherent objects. Well, if you work in the generalities of quasi-compact quasi-coherent schemes. As I mentioned before, if scheme is locally coherent, then the pseudo-coherent is not very interesting. That's the same as the d minus of the x. So another thing that I want to formulate, I don't want to prove, because the proof is quite similar to the proof of the previous statement. So that f and x prime to the x be a map of schemes. F and G are two complexes of OX modules, and as before, suppose one of the following two hypotheses is satisfied. Suppose one satisfied. So one is f is perfect, and two, the Tor dimension of f is finite. F is pseudo-coherent, and G is locally bounded below. Very much as before. So then, there is an isomorphism. So we take the direct pullback of the R home, local home, between F and G, and then there is a map, which is an isomorphism, to the R home x prime, and then you just take this pullback and put it inside. So usually this is not the property of the pullback, or you cannot say that this holds in very generality, but let's actually notice that the condition 1, when f is perfect, is more or less a trivial observation, right? You can kind of do the same proof as before, so we introduce this subcategory, right? So you fix object G with given properties, you consider subcategory of all the f's where this is an isomorphism, you check all the properties as before, but I want to say that one is actually trivial, right? Because if f is perfect, then the R home between f and G, you can compute this as tensor product of the f dual and G. And for the tensor products, that's a very simple property that the pullback can use to the tensor product. So, and when one is easily follows from what we know already about the perfect things, but two is I would say interesting, right? So,
what's Tor dimension of a map?
I defined Tor dimension before when we discussed the kind of the Tor
Of the map?
yeah, because a special case. So you have
X.
yeah, you have kind of object and also a map. You can take a trivial map or trivial object. So that's the case of OX, trivial object. And also, I think some of you took commutative algebra class with me, and then we put the statement when you kind of have a home between two modules, the first module is finally presented, and then we take a kind of tensor product with for example, we were interested when the optimization commutes with the homes. So more generally, you can take a flat tensor product with some ring, right? And we saw that if the first argument is finally presented, right? So then we can move this tensor product with the flat extension of algebra inside. And you can see that this kind of special case of this very general statement, right? Because in that case, when you kind of try to do this argument that I've done in the previous proposition for the G, the parameter A is just 0, and the parameter for the quasi-coherence is finally presented, so this is kind of just 1. So that would be a special case, and that proof would be specialized. Well, the proof actually quite different, so that proof we use something like 5 lemma, etc., etc. So, and here, another more general statement is proof using trivial categories. Okay, just to compare this with something that we've done before. So, okay, so this is again exercise. I kind of try to modify the previous proof to solve this exercise. And now I want to formulate very useful general lemma. So let f from the x to the y be quasi-compact, quasi-separated morphism of metal strips. So then the derived functor of the push forward preserves coproducts. In other words, I'm used with direct sums. Well, the proof that I'm going to do is not really a complete proof. I want to derive the statement in this generality from the statement about the product or just sheaves. And I kind of assume that we know this property for the sheaves, not for the complex from the course of algebraic geometry. Okay, so let me fix some coproduct. So let me write E. This is direct sum of the EIs. That's a coproduct in the D of X. Now, of course, we have a natural map from the direct sum of the direct images of the EI to the, no, that's just from the universal property of the coproduct. So I want to show that this canonical map is an quasi-isomorphism. Well, since again the standard argument, we can notice that the both sides commute with the shifts, so it's enough to show that this map induces isomorphism on the zeros cohomology. So it is enough. So maybe let's call this map phi. So it's enough to show that H0 of phi is an isomorphism. And also, well, that's a map on the scheme Y, and being an isomorphism is a local property. So without loss of generality, since we're checking some local property, Y is affine. Okay, so then I'm using that if I want to compute, say, Ri f lower star of the E, I can identify this with the Ri f lower star, and then I take the interpolation. Right, so that was the general property that we proved on the previous lecture. So another reduction is that without loss of generality, we can think about this E as a bounded below. So that's a bounded below. But for the bounded below, I have a convergent spectral sequence. This says R, P, F, lower star, H, Q of E. This converges to the R, P plus Q, F, lower star of E.
So why we can assume it's
What?
because of this isomorphism?
Bounded below?
Yeah.
Yeah, because you can compute this thing as the right hand side of this identity. Yeah, and I'm using bounded below to say that there is convergent spectral sequence. If this is not bounded below, you can't claim this is convergent. Okay, so let me say, so spectral sequence like this is convergent. Thus, the result follows from the following observation, that if you take, say, R, P, F, lower star, apply this to the direct sum of the EIs, then this is isomorphic to the direct sum of the R, P, F, lower star, EI, right, where EI is not complexes but just quasi-coherent sheaves on the X. And that's I'm not going to prove that this is true for sheaves, because I can assume that you know this from algebraic geometry. If you don't know this kind of exercise and just kind of topology maybe. Maybe you can ask this question when this is true for a map of topological spaces. Yeah, you'll get some property which is usually which is satisfied when the map is quasi-compact, quasi-separated. Okay. So next little topic is the so-called projection formula. You probably know underwrite version of the projection formula, and I'm not going to again prove this. Just rely on your knowledge of algebraic geometry, but I'm going to formulate the statement. So the underwrite version is the following proposition. So let f from x to the y be a map of ringed spaces let's take f to be a module on x, g is a module on y. So there is a natural homomorphism, let me for shortness write natural map from the f lower star applied to the f, then I take a tensor product over OY with G, then let's call this map phi, to the f lower star applied to the tensor product, so f tensor product over OX, f upper star. So this natural map, which is of course this is functorial in the both arguments. So the map which I call phi, so phi is an isomorphism in the following cases. The first case is that G is locally free of finite rank. And this is usually the case that is proved in the most textbooks in algebraic geometry. But there is, for us, the second case is a little bit more interesting. So f is quasi-compact, quasi-separated map of schemes. So I assume, of course, that X and Y in the case 2 are schemes, and this is a very special map of schemes. The F and G, the OX modules, in this case, are quasi-coherent. Quasi-coherent. And G is flat over O. So then in this case, this is another isomorphism. So I'm not doing this proof. I assume that we know this from algebraic geometry. Yeah, maybe the last remark, how to get this map. I don't do the full proof, but do we understand why we have this natural map phi in this direction between these two objects?
It follows like from junction.
Yeah, so by the adjunction, if you want to kind of get a map like this, you can take this F lower star, the left adjoint will be the F with the upper star, right? So you'll get the, and the F upper star, of course, commutes with the tensor product. So you get F upper star, so maybe I write this instead of just saying. So you'll get F upper star applied to the F lower star of F, tensor product is G, right? So this is mapped to the F tensor product with the F upper star of G, right? So produce that map phi is the same as producing this map. But this you can say this is isomorphic to the F upper star, F lower star of F, tensor product with G. And the map here.
No, tensor product is F upper star.
Yeah, thank you.
And then just junction.
Yeah, so this is F upper star of G. And then for this map, kind of there is the counit of the adjunction for this adjunction, so there's a map to the F. So, F, well, maybe instead of writing one more formula, I just write map like this, and write this as an epsilon tensor identity, where the epsilon is just the counit of the adjunction for these two functors. Okay, so let's take a 10 minutes break. And we'll do the draft version of this formula.
Можно вас спросить о домашке? Что такое I-torsion модуль для идеала дни? Это при умножении на некоторую степень и любой элемент зануляется? Или просто при умножении на и весь модуль зануляется?
Нет, это именно для степеней. То есть, грубо говоря, вы берете какой-то элемент модуля, да, и тогда вы можете подобрать соответствующую степень идеала, что идеал этой степени на этот элемент действует нулем.
Хорошо. Просто на этот text project, это, кажется, называется I-power torsion.
Да, там они как бы развели теорию всякую, которой в классической литературе нет, потому что они решили, что определение классическое не совсем хорошее, потому что там не совсем производная версия не совсем хорошая, поэтому я сразу стартую с другого определения. Но мне кажется, что там я сказал, что кольцо Ньютона в этой задаче.
Да.
Но в Ньютоновом кольце все определения должны совпадать.
Хорошо.
А вот что такое квазиотделимая схема?
Квазиотделимая?
Да.
Пересечение двух открытых афин?
Нет.
Нет, это вроде полуотделимое.
Нет, пересечение любых двух является конечным объединением открытых афин.
Нет, в определении, по-моему, что пересечение квазикомпактного является квазикомпактным.
Но это равносильно.
Да. Но или по-другому можно сказать, что у вас есть диагональный морфизм, вот если есть морфизм какой-то, если есть соответствующий диагональный морфизм, он должен быть квазикомпактным.
Да.
Так.
Это квази-отделимое.
Да.
Там контрпример красивый. Такая бесконечная мерная версия там двух плоскостей, которые поточат. Ну, склеены всю эту. А можно еще спросить? В первой задаче там нужно для любого кольца, ну, там, где нужно построить какой-то бесконечный, неограниченный комплекс.
Из инъективных,
Да, который-
Ну, конечно, не для любого, это надо как бы.
То
Я
есть-
плохо наформулировал задачу, немного надо привести пример кольца и комплекса.
А.
Для любого не получится, потому что, например, кольцо бывает такое.
Ну да.
Там такого.
Мгм. Хорошо.
А мы вот при доказательстве утверждений на прошлой лекции сейчас ни разу не использовали в явном виде, что схема квазиотделима. То есть это где-то
Какого утверждения?
ни в каком, где в условии формулируется, что схема квазикомпактная и квазиотделимая. Там вот квазикомпактность мы использовали, когда конечное покрытие выбирали, а вот квазиотделимость никак нигде.
Не, ну она у тебя спрятана. Вот,
Да, то есть-
например, вот по последнему утверждению, что мы доказывали, я в итоге сослался на утверждение, что это верно для упразднения пучков.
Да.
И там понадобится квазиотделимость.
То есть это в каких-то недоказанных утверждениях из алгебраической геометрии
Да.
спрятано. А вот еще вы говорили, что композиция двух производных функторов, производный функтор от композиции. И это доказывается, вы сказали, что образ К инъективный, резольвенты К инъективны.
Ну, коинвективный объект, коинвективный, да.
Да, это при любом функторе. То есть это в каком смысле образ К инъективного, К инъективный?
Нет, там суть в том, что композиция двух производных равна производному, если вот там RF композиция с RG равен RF композиция с G, только если при G К-инъективный объект переходит в К-инъективный.
Да,
такая-
это как раз ясно, потому что G это просто что, открытое вложение, да?
Ну да, вот нам это понятно.
Да.
При
И
открытом
тогда можно
вложении-
просто заметить, например, таким способом, чисто гармонического алгебры, что ты просто, у вас будет сопряженный функтор будет точен, и тогда это означает, что коинъективность будет сохраняться этим функтором.
Сейчас там я не провел бы точно. Нет.
Но нет, да, утверждение, что производная прямой образ сохраняет коинъективность, но, конечно, верно гораздо больше общности, чем просто для финных открытых вложений. Я просто боюсь сказать неправду, что это верно всегда. Но оно, я думаю, верно только для квазикомпактных, квазиотделимых приложений. Но, может быть, это вообще всегда верно. Вот, но то, что это...
Ну, для квазикомпактных, то есть в такой вот общности достаточно большого, но верно.
Да, да. Что-то мне кажется, я в какой-то момент это где-то записывал, доказывал, а потом я решил это не рассказывать. Да, потому что я решил это не рассказывать, я это в записках у меня этого нет. В общем, я это проверял, и, по-моему, в хорошей торговности про квазикомпактных, квазиотделимых это точно верно. Может быть, она верна и вообще для любого морфизма схем, но я просто сходу не помню. Это, кстати, в какой-то момент мы понадобилось проверить, чтобы сделать четвертое домашнее задание. Там в одной задаче это спрятано. Поэтому надо придется подумать. Но это не сложно. Я как бы все детали проверил, мне займет 3 странички. прошлое задание, там 11 задач, но там пара получилась довольно сложно, можно только. Поэтому как бы, я, наверное, добавлю еще, может, одну-две, придумаю 3 задачи попроще, чтобы у вас был выбор. Я постараюсь сделать там.
Какие там самые сложные?
Ну, там есть вот эта такая задача, что когда у вас curve совпадает с S-curve, что тогда вы любой конечный векторный модуль можете накрыть векторным освоением, грубо говоря.
Когда перф совпадает с перф.
Да. Это не очень просто доказать. И еще, мне кажется, сложная задача, там всякие, там последние, по-моему, задачи, которые написаны по примеру, надо построить, что там спрашивается верно, значит, спрашивать, что написано по примеру.
О, это хорошо. Точно. Потому что мне казалось, что там вот предпоследнее, там спрашивается верно, а мне казалось, что вообще правда.
Какое-то произведение, все это самое, квазикогерентных, слово квазикогерентное, нет, это не так.
Да. Ужас. Зачем ты вот такой? С такими схемами нужно работать. Когда это верно?
При этом понятное дело, что произведение категории квазикогерентное, другое произведение, оно, разумеется, верно, потому что категория перпендикуляр.
Слушай, почему это другое произведение? То есть потому что мы берем резолент, это... Нет, сейчас, а почему?
Точно, про резонанты надо спросить вопрос.
Почему это другое произведение? То есть что ломается?
Ну, оно априори другое.
Это же просто произведение пучков. Что там? Почему? То есть, типа, вложение не коммутирует с произведением пучков.
Нет.
Ну, с конечным коммутируешь, да?
Ну, конечно, конечно.
Ну да.
Ну, конечно, потому что это там будет произведение, да, а это будет там его обвинение восприемных.
Ну да, действительно.
Нет, ну это, кстати, ну не то, что прям какой-то чудовищно удивительный результат. Я когда элементарно грамматическую алгебру читаю, то я там тоже такую задачу задаю. Там, по-моему, категория всех авиагрупп, категория авиагрупп кручения, и там тоже можно проверить, ну, очевидно, более-менее, что бесконечное там произведение авиагрупп кручения, оно не является обязательно группой кручения, но, тем не менее, в авиагруппах кручения есть произведение. Но которая, грубо говоря, устроена так, что вы берете произведение в авиагруппах, а потом просто берете под группу кручения. И здесь в каком-то смысле то же самое. Вы можете взять квазикогерентные пучки, перемножить их в X-модулях, да.
Ну, понятно, взять квазиратор, или как он там
Квазигератор, да.
Квазикогератор. Ну, это да. И это будет как распределение, да?
Ну, это обязано совпасть с определением, просто, это следует из того, что это следует, что это право следования.
Что продукт инъективных X-модулей не вял?
Да.
Ужас.
Кстати, вот с композицией, там, если не бесконечно в обе стороны производная категория ограниченная была бы, там было бы все сильно проще, потому что брали бы просто вялый резольвент, а прямой образ вялый, оно вялое.
Да.
А тут все усложнено за счет бесконечности вниз.
Ну, нет, ну, если как бы выбирать либо d плюс, либо d минус, то оно все становится сильно проще.
Да.
Просто там посчитайте мид мандамальный, там никаких таких теоретических заморочек никаких нет, все хорошо работает.
А нет такого понятия, как к-вялая резольвента или что-то такое?
Нет, я такого не знаю.
А зачем вообще просто? У нас же К-инъективное, они вообще не инъективные. Оно К-инъективное называется, потому что оно так же вот как инъективное работает, то есть для каких там для левоточных функторов. Поэтому оно К-инъективное, просто чтобы это были резольвенты для левоточных функторов.
Ну, есть же К-плоские.
Ну да, это странно. Ну, просто вялые же резольвенты, они тоже используются только для этого, для того, для чего можно инъективно использовать.
Ну, был бы образ К-вялой резольвента,
Кстати,
К-вялая,
да,
вот такое.
Вот, да, кстати, странно. Честно, что это?
Может быть, я не помню. Посмотрите, с Полтенстейна 88 года, нет ли у него там К по объекту? Я не помню просто. Но я таким никогда не пользуюсь.
что это правильно.
Не, ну как ты определишь?
Ну,
У тебя же вялость определяется термином в сечении каких-то.
да, ну тут
У
скорее
тебя комплекс, но
вопрос про то, вот,
можно, конечно.
вот какая вот там в чем прикол, зачем нам вялость вообще нужна? Нужно, чтобы в каком-то моменте, когда там пропадает эмиссивность, вот, когда вот мы считаем, это, что не пуш-форвард или в пулбеке,
На пуш-форварде.
при пуш-форварде пропадает эмиссивность, у нас сохраняется вялость.
Да, но вяло они являются цикличными для глобального сечения и для пуш-форварда.
Да.
Вот. Соответственно, там по помощи условия должны быть.
Сейчас, а вот вопрос, какая эмиссивная изолента, если заслушать, вы говорите, если пуш-форвард сделать какая эмиссивная изолента, вы говорите, что это, ну, не фашер всегда, да?
Я просто не помню.
Какая
Для
эмиссивная?
квазиизображения должно быть верно.
Да. Ну, для этого тоже, да. Пуш-форвард какая эмиссивная будет калял всегда. Ну, правда.
Ну, это ведь, вот если категория D+, там же конъюнктивная, это просто инъективная.
Да.
А
Ну,
образ,
конъюнктивная.
да, но образ, прямой образ инъективный, это ведь не всегда инъективная. Она просто вялой становится, она не обязательно инъективная.
Да, но она, конечно, но она остается конъюнктивной. Или
Не.
вяло не всегда, да, конъюнктивной.
Нет, нет, но у вас как будто условия на комплекс совокупности.
Но не конъюнктивный. То есть можно просто взять один инъективный модуль, он инъективный, взять его прямой образ, он же не обязательно инъективный будет. Но при этом вялым он будет только.
Это правда, да. Да, я сейчас вспоминаю. На правильное утверждение не то, что конъюнктивность сохранится. Конъюнктивность сохранится вот именно в том случае, в этом приложении, которое я доказывал. А общее утверждение, которое верно для квазикомпактных, квазиделимых, это как раз то, что вы берете прямой образ конъюнктивного, и он будет гамма-цикличным. Вот такое утверждение будет верно. Ну, то есть это как раз есть.
Да, но это в смысле глобальный сечение.
Да, не конъюнктивность сохранится, а именно конъюнктивность обоими относительно. Это совершенно верно.
То есть конъюнктивный переходит в калял.
Вот я сейчас.
Скажи, что такое кавиал?
Ну вот у Герфандамани упоминаются камятькие резольвенты, что такие
Ну,
бывают.
видимо, это плотно стоит. Камять.
Кософт.
Я не знал, что говорит, там нормально есть что-то.
Нет, вот просто что бывает такое, то есть там буквально в упражнениях он обсуждает это.
Я думаю, что если такое бывает, то это придумал Спотенстейн, и это написано в его статье 88 года.
So let's continue and prove the direct version of the projection formula.
So I'm going to formulate this theorem as analog of the previous proposition, quite general form. So let F be a map of two ring spaces. So be a map of ring spaces. So F as before it was a module, now this is a complex of all x modules, and G is complex of all y modules. So then there is, as before, natural transformation. Derived factor of the push forward applied to the F, and then the derived tensor product with the G. So that's the tensor product of Y. This is mapped to the derived push forward of the F tensor product, derived tensor product of the X with the derived pullback of the G. Well, there's natural transformation, functors, factorial, well, this is very factorial in FMG. And maybe, again, I call this phi. I don't think this will be a source of any confusion. So the map phi is an isomorphism, or quasi-isomorphism. Quasi-isomorphism if, well, if one of the following conditions is satisfied. So first condition is kind of analog of the previous one. So G is perfect over Y. And the second condition is F is quasi-compact, quasi-separated map of schemes. And F has quasi-coherent cohomology and G has quasi-coherent cohomology. So notice that if you compare this with condition 2, I don't need any flatness requirement for the G. So that is because for the G I apply the derived factor of pullback. Okay, so for the proof, the existence of this map you can kind of do in the same way, right? So you use the adjunction, you take this. That computation works if you put everywhere derived functors. Right? So in this way you get the map. Okay, so that's the map. Now, again, we want to check that the map between two complexes on Y is quasi-isomorphism, right? So, or isomorphism and cohomology. So this is local on the Y, and without loss of generality, I'm going to assume that Y is affine. So then we fix argument F. So fix F and let T be a subcategory in the D of Y. So this is the full subcategory. Category of the objects in G, for which Y is an isomorphism or quasi-isomorphism. Quasi-isomorphism. Okay. So what we can say about this T? Oh, it's clearly closed under shifts, and it's also quite clearly closed under kind of taking triangles, right? So if you have on two vertices, right? So left-hand side and the right-hand side is the triangulated functors, right? If you have a distinguished triangle on two vertices, that's an isomorphism. Then the third vertex also an isomorphism. So T is a triangulated subcategory. Okay, so that's a triangulated subcategory. The structure sheaf O, Y. Well, this is definitely in the T. Right? If you look at the formula, so this is all the G's. So if this is just a structure sheaf, then this pullback, derived pullback, is again a structure sheaf. Right, so since the structure sheaf is flat, that you don't need to derive this, and the pullback of a structure sheaf is structure sheaf. So this tensor product doesn't do anything. So this will be a direct image of the F, and of course here this will be direct image of the F. So for when G is a structure sheaf, clearly everything is satisfied. Phi is just the identity. Okay, and then we can also we look at this for f is fixed, we look at these functors as the functors of g, and this functors preserves coproducts. This functor preserves coproducts since it's just a tensor product, and this also pullback preserves coproduct because this is this is left adjoint, right? And tensor product again preserves coproduct. So let me write it like this: since derived pullback and tensor product, and as we saw before, derived push forward preserve direct sums, coproducts. Push forward by the previous system.
I just don't understand why we need, but we need it.
We need this, yes, on the right hand side. So the subcategory T is localizing. Okay, so then the final remark is that if we look at the set, which is just a structure shift, right? Remember that y in this case is affine, so you take a structure shift and take all its shifts by some integer number. Right, so this set compactly generates d of y, which is in this case just the right category of R modules where spec R is equal to y.
Did they prove it?
Yeah, it was kind of like an example when they introduced notion of compactly generated.
They proved it for ring. Ah, it's a fact, yeah, of course.
Yeah, for ring, yes. Okay, so then the localizing closure of the structure shift, right? So the structure shift is in T. T is localizing, so the whole localizing closure of the structure shift is some subcategory inside T, right? But what we did before. Now T is of course just some category by definition in the d of y, but we can also notice that this is localizing closure of the of one. I think that at some point I gave this as an exercise, but if you use this theory of Thomasson localization, that's trivial. You actually prove this, right? Because if you have this set that compactly generates some category, then the log of the set, and in this case, the log of this set is the same as log of this object, just coincide in the category.
I suppose we proved it like when we consider some compactly generates category, and there is compact objects that generate some log, and then we just consider. I think we proved kind of the same.
Yeah, we proved the general statement, and this general statement is sometimes called Thomasson localization, where you can take a closure by log of some set of compact objects. So in this case, one of the theorems that we proved there is that when you
but why coincide with compact generators then this
yes,
the same.
so then the log is the same as the category. Yeah, so combining this this statement, which is by Thomasson localization, we can say that the log of y is the d of y, right? So in particular, we see that the c is the d of y, right? So g could be any object in this category, and f is also any. We just fix f.
So we proved it for any d of y. Why we need these conditions? G is perfect or f is quasi-compact, quasi-separated in this case.
Well, it's again the question of the hidden use of the quasi-compact, quasi-separated. Well, for example, I use f is quasi-compact, quasi-separated is used here, right, to say this is preserves direct sums.
Yes, that's true. So first one we didn't prove.
The first one we didn't prove, but I think that's easy by using exactly the same argument, right? You again consider the subcategory T of this sort, right? So F is anything, and if you don't know that it's quasi-compact, quasi-separated, you cannot say that this preserves the coproducts, right? So you cannot say that T is localizing, but you can notice that T is thick.
Mm-hmm.
It still contains the structure sheaf, it's thick, so it contains every perfect object.
That's true. Yeah,
So
also,
to be completely formal, let me say that this is the proof of 2, right? And exercise show 1, which is I kind of just solve this exercise, right? It's just simple variation of this. Okay, so that's the proof of the derived projection formula. And finally, the last topic in this whole chapter, I'm going to call this base change. Base change and unit map. Okay, so I start with the definition of two Tor-independent morphisms. So two morphisms usually this is kind of almost immediately completed to the pullback diagram. So let me write this morphisms like this. I have S prime map U to the S and X map by the map F to the S. So because later it will be the context of the Cartesian square, so I'm going to write it from the beginning like this. So two morphisms of schemes are Tor independent. If I have the following property, so if Tor with the index I over the local ring OS little s between the OS prime little s prime OX little x is equal to 0 for any I positive. For any for all points, so in this case of course S prime is a point in the S prime, little x is a point in the X, such that U applied to the S prime is equal to the S, and this is also equal to the F applied to the little x. And there is also, I think, something missing. So this Tor I has to be 0 for any index I, and also for any point little s in the S. So that's the definition of a Tor-independent morphisms. And of course, what would be the standard example? Well, you take F to be anything, and you take U to be flat. So the flat base change is an example with some other morphism is an example of Tor-independent
I
morphism.
suppose usual flat base shape. Isn't it should be like substance proper?
No. Okay. The next lemma I want to leave as an exercise, just another way to, it's kind of simple exercise in commutative algebra, just a way to reformulate this definition. So let me, for shortness, write these two maps in one line. So let U be a map from the S prime to the S, and there is also map F from the X to the S. So let this be maps of schemes. So then the following are equivalent. So the first condition is that U and F are Tor independent. Right, so the second condition, now it's a kind of similar condition, but for affine neighborhoods. So for O S prime in the scheme S prime and X in the scheme X, such that U s prime is equal to the s is equal to the f of x. That's all. The condition as before, but then we claim that there are open affine neighborhoods spec R in the x. Oh, that's an affine neighborhood of the point x, and then there is of the point. Sorry, this is not in the x, this is in the s. This is in the s, so this is affine neighborhood of the little s. Then there is spec A, which is in the pre-image of the under f of the spec R. And so that's an affine neighborhood of the x. And also there is spec R prime, which is in the pre-image under the map U of the spec R. So that's an affine open neighborhood of the S prime. Okay, so such that if you choose this affine open neighborhoods, then the same condition for the torus is satisfied. Tor I between R prime and A is equal to 0 for any I positive. So for any 3 points like this, there are open affine neighborhoods with these properties. And condition 3, for all open affine subschemes, spec R in the S, spec A in the inverse image of the spec R under the map F, and spec R prime, which is in the inverse image of the U under the spec R. So the condition with the Tor, as before, is satisfied. Okay. Well, since this proof is just some technical details in the more or less standard algebraic geometry, that is an exercise. Okay. So now let me look at the following commutative diagram of schemes. So it will be used several times by computations in this subsection. So I have x, which is mapped to the x to the s with the map f, and this kind of this map, which is almost like a base change. I don't assume this is Cartesian at the moment. So like a base change square, but I don't say that this is Cartesian. So just the commutative diagram of schemes. Commutative diagram of schemes. And also let me fix an object E, which is in the D of the S prime, and object F in the D of X. So now I want to define the unit map. The unit map is the following composition. And I want to call this unit map always eta. That will be my standard notation for the unit map. So I take the push forward. Oh, everything is derived, so push forward of the E, take a tensor product with the push forward with the map F of the object F. Right, so there will be several applications of the projection formula. Well, first of all, there is this unit of the adjunction, and I can write this. Yeah, and also in this square, I want to fix notation, so this diagonal map, which is composition of the U prime and F, or F prime and U, I'm going to call this map G. So then, they will push forward along map G, then pull back with the map G. And so this map I just get by the adjunction. So the argument inside this push forward, pull back is the same. Yeah, so of course the tensor product is derived. I forgot to write this.
Okay.
So then, I keep the direct push forward by the G, and when I apply the direct pull back to the tensor product, I'm used to the tensor products. Right? So then I can write this, so that would be, so that, well, for the first argument, that would be the push forward with the U, and then pull back with the G. But now for this G, I want to use this as a composition of the U and F prime. So let me write this as the push forward along F prime, push forward along U, and then they keep the, pull back along F prime, pull back along U, and then let me keep this push forward with the U prime on the object. Okay? So the right as a product. Now. Yeah, now I want to apply this pullback with the G, but I want to use this presentation as another composition of the U prime and F. So this will be pullback with the U prime, pullback with the F, and then push forward with the F. Okay. And all these computations are trivial, but kind of annoying because we work on the wrong formulas. So then I have a map, so I need to look at this adjunction and also this adjunction. Right? So then I can use the counter of this adjunction to write this as the RG rho star, which is applied to the pullback along the F prime, which is applied now just to the E, right? Because here is this composition of factors, I just used the counter of the adjunction, and the same for the second argument in the tensor product. So this will be pullback with the U prime of the F. Okay, so this composition is called the Q-unit map. The reason to call this a Q-unit map, just note if you're not satisfied with the formal definition, is the following remark. So remark, if you take S to be just the spec of the field, so then all maps, right, so U and F, and hence well, let me just say that, and not then, but, well then, U and F are flat. Let's see, is this enough for what I want to say? So then the map that we get in this way will be R U lower star E. So then the product F lower star F, R G lower star F prime upper star E, then the product with the U prime upper star F. Okay.
We need U and F to be flat.
Well, because I want the simplest possible case, so let me also assume that x prime is the product of the x and s prime of the s, right? So then this will be Cartesian square, and the base change of the flat is flat.
Okay, I think we still need right to area or right tensor product.
Here?
Yes.
Well, I don't think that you need to derive this, right? Because
We know nothing about E and F, or maybe not.
yeah, I think we cannot say that this tensor product. What we can say is that we can take this underived tensor product, right, and do the same computation, right? So if I erase the derived tensor product there, this still works. So I still get this map, so kind of modified map, the simplest possible map that I can get. Because the point is that if I now look at this map, well, kind of erase all the derived stuff and where I have the tensor products and the pullbacks, I have only derived push forward. And then I look at the nth homology, then nth homology applied to this map give me the following. I'll get direct sum of the hi s prime e, the tensor product homology with the index j x f. So tensor product over field k, so I plus j is equal to the n, and this will be a map. So this will be a map to the hn x prime f prime upper star of the e tensor product the u prime star the f. Well, of course, in this case, there can be a direct product. This is just an ordinary product, right? This is just over the field. But here, this is over x prime. So potentially, this could be a direct product. But well, I don't really care. I can, if you wish, I can write the direct product here and here, right? Get a little bit more complicated formula. But the idea is if you work over a field, this is kind of the standard map that you want to call the unit map, right? From the product of cohomology to the cohomology. And this is the reason why in this situation we can also call this ethetic unit map. So that's the explanation. Okay, so I introduced the notion of the Thorne dependence, I introduced the unit map, and I also want to introduce the notion of the base change map.
I think we always have map from this derived tensor product to non-derived, because we can have
Sure.
a map from flat resolution to
Yes, yes. No, because it's not really a theorem or something. It's just a remark about why it makes sense to call this map a unit map.
Mhm.
So I think for this remark, it's not very important. What do I write this derived, or I just keep this derived as a product? Well, with the derived tensor product, it has more chances to actually be an isomorphism. I think that's the reason to write the derived. Okay, so the base change map. So let me kind of finish this remark here, and I continue to assume that I have this diagram with the same notation as before. So, and for this diagram, I have the base change map, the base change map. And again, I want to fix standard, well, not standard, but fix some notation for this map. I'm going to call this theta. This will be kind of natural transformation of functors from the derived pullback of the along map U, composition with the derived push forward with the F, and this is a map to the derived push forward with the F prime, composition with the derived pullback with the U prime. So that's a kind of natural transformation, or trinatural transformation of translated functors, right? And from the functors from the derived category of the x to the derived category of the s prime. Okay, how we can get this map? This is again by adjunction. So by adjunction, giving theta is equivalent to giving a map like this. So let me write the derived push forward for the L prime, derived push forward for the F, derived pullback for the F, which is equal to the derived pullback with the F prime, derived pullback with the U, derived push forward with the F. And this is mapped, maybe I write it here, so this is mapped. I'll just explain this in a minute, let me just finish the formula. To the push forward of the U prime with a star. Right? So if I have a map like this, well, I can look at this functor with the F prime, and by the adjunction, I need to write it here, right? Here, but with the F prime upper star, right? So by the adjunction, I need to give a map like this.
So why is this equality here?
Yeah, and this is just because you look at this part, and you look at this part, and that's the same map. And again, I'm using the kind of, if you take push forward, it the derived functor is the composition of the derived functors. Okay, so this is how we can get this map theta. So we kind of, right, so here what we have, sorry, yeah, so this, yeah, so why I need to rewrite it like this, right? So I want to produce a map from the, well, if I just think about the terms of the adjunctions, I need to produce a map like this, which I can rewrite like this, right? But this map is easy to produce, right? Because I have a map, which is again the counit of the adjunction, right? So this is a map to the identity, right? And then I take the kind of composition with the derived so with the derived pullback along the U prime, and then I get this map.
So, and how we produce the theta from it?
By the adjunction, I'm saying that if you want to produce a map like this, you take this functor, and by adjunction you put it here, but with the upper star. This is what I have here, right? To produce this map, I need to produce this map, but that's the same as this thing. So I need to produce this map, and this I can produce if I just apply L U prime upper star to this counit of the adjunction.
Yeah, but isn't it in the other direction? So can you? Yeah.
Why this is another direction? This is just the adjunction. So home from this to this is equal to the home from this to this. This is the same direction.
Oh yeah, this. Yeah.
Yeah, and so there is an annoying exercise that this is not the unique way to produce this base change, right? You can also, let me formulate this as a remark. So, remark, we can also define eta by adjunction, so using R F lower star, this is mapped to the R U lower star, R F upper star, lower star, so the draft U prime upper star, which is the same thing as the R F lower star R U lower star prime U prime upper star. So this identity by the same reasons as before, and the map we can get again by taking the unit of the junction for these two functors and then recomposing this with the RF low star, right? If I get this map, so then what? Yeah, so I can produce this map, and I also want to say that I can get map like that, but how? So I need to take this RU, right, and by the adjunction move it here with the RU upper star, right? That will be kind of another map theta, right? So another version of theta, which acts from the same kind of composition of functors to the same composition of functors. So exercise is to show that these two definitions are coincide. So exercise. Two definitions of theta are equivalent. Okay, so finally the main theorem about all this.
Yeah, why you say eta? Isn't it theta?
Yeah, so there's two definitions of theta equivalent. So let, as before, get the same diagram. So x prime, x, O prime, f, s, s prime. So, but now I want to assume this is Cartesian diagram mainly. So let this thing be a Cartesian diagram of two web, in other words, of schemes. So all schemes are quasi-separated F and U are quasi-compact, quasi-separated. So then the following are equivalent. So the first condition, the base change map theta is an isomorphism. So condition 2. So the unit map theta is an isomorphism. Well, here, since I define this eta when I use some E and F, so just briefly write that this is for all objects E and F. And 3, U and F are Tor independent. So this kind of the, if you know the flat base change, this is the ultimate version of the base change, right? So this is criterion. If you can have Tor independent, for example, flat base change, then you have the base change isomorphism. Also you have a Kuhn formula. But if you have base change isomorphism, that means that you have actually Tor independent morphisms. The most general formula of the base change that I know. The proof of this thing is kind of complicated. It's been divided into several steps. So let me start with 1 implies 2, which is not so hard. This is essentially done by looking at one commutative diagram of functors. So let me start with the map eta, so repeating map eta. And then I also have two quasi-isomorphisms, which are just given by the projection formula in both cases. So this will be like this. Right, so you can notice that this is indeed just the isomorphism by projection formula for the U low star. And then in the other direction, which is also in isomorphism, I look at the R U low star. Then the product of the E and the R F prime low star, L prime upper star F. Right. So to understand this, I think this is just, I take this map G, look at the diagram. So remember that always the map G is just the composition in this diagram, right? So I have this map to G, and I can think about this as the push forward along F prime, push forward along U, right? So there is kind of push forward along U instance here. So this thing is kind of independently. This is R U prime, R F, R U, R F, right? So I keep this R U prime and I use the projection formula for the F prime, and this is what you get if you use the projection formula. I think everything is fine. Okay. Now this map that we have here, right? What is this actually? Well, this is functor R U prime, which I applied to the tensor product with E to the map theta. Right? So this map, there's a kind of canonical base chain map here, theta, and this is just the result of application of this tensor product with U and the push forward. But in one, I assume that theta is an isomorphism, right? Hence, this is an isomorphism, these two maps are isomorphisms, hence the eta is an isomorphism. So that's the end of the proof that one implies two. That was simple. But also important remark here. If R U lower star is conservative, then clearly by this proof, 1 is equivalent to 2. So in the special case of a conservative functor, these two conditions are equivalent.
Isn't should be yet tensor product with anything also conservative? Or it's always conservative? I suppose it's not.
Well, so what we need to show? We need to show that 2 implies 1, right?
Yeah.
So we have this argument for any E, right? So if we assume 2, then this is for any E. In particular, this is for the structure sheaf.
Yeah, you're right. Mm-hmm.
What is a conservative?
Like I can answer, like it reflects isomorphisms, but reflects this means that you have a map. You apply a functor to this map, right? If this is an isomorphism, then the map you started with is an isomorphism. Okay, so that was the easy part of the proof. The other two directions are a little bit harder, not very hard, but just a little bit. So let's go in the 3 implies 1. So it will take a while. And here I'm going to have 2 steps. And before these 2 steps, I'm going to formulate an independent lemma, which also will be useful later. So in this lemma, I assume that f from the x to the s, so this is a quasi-compact, quasi-separated map of schemes, right? So if, well, I want to formulate this shorter, so 2 conditions. If one of the following 2 conditions is satisfied, if first f is open, immersion, or second condition, f is affine, okay, the special cases, So then R F lower star is conservative. Conservative. Okay. So
If one of them is the
yeah, if one of these two conditions satisfied, then the push forward is conservative functor.
So can you please say again why then the product with E is conservative?
Well, because in the assumption, if when you go from 2 to 1, right, I just erased this condition, right, so this is for any E and F,
Yeah.
in particular for E, which is a structure shift.
Okay.
Yeah, so let's prove two parts, but before this, let me fix some notation. So let me say that alpha, which is a map from F to the G, is a morphism map in the D of X. Okay, so let's look at the case of the open immersion, the first case. Okay, so I claim the following. For an open immersion, I have the counit of the adjunction, so the push forward composition, sorry, pull back composition is push forward to the identity. This is an isomorphism of functors. Right? Well, that's easy to show. So let me, in parentheses, write a little proof. So if, say, F, some object on which I wanted to draw this isomorphism, let me fix in k-injective resolution. So F is k-injective resolution I. K-injective resolution. Okay, so then when you compute the left-hand side, for the object F, then since I compute the push forward with the k-injective resolution, I can write this as the F pullback, F push forward applied to the I. Right? Well, I can erase this left-right functor because in this case F is open immersion, this is a flat map, we don't need to derive this. And for the F low star, this is how you compute our F low star with the injective resolution. But now this is, of course, isomorphic to the I, right? So this is just the application of these two functors, this compositional functors to this complex stormways. But for an open, if you just look at the underderived version, this is the identity, which is kind of well-known fact from algebraic geometry. So we're almost done with this proof, right? Because now I can write alpha as the L upper star R F lower star applied to the alpha, right, by this identity, and so alpha is an isomorphism if push forward R F lower star alpha is an isomorphism, right? If this term is an isomorphism, then the pullback is also an isomorphism. If you apply any functor to any isomorphism, you get an isomorphism. So that's the proof in the part 1. Now for 2. Now F is affine. Again, now this is kind of the standard game. So the statement is local on S. So without loss of generality, S is affine. Right, so the map is also affine. So hence X is affine. So we kind of doing some commutative algebra. Okay, so let me use diagram that I was using in the previous lecture, and also prove the general version today. Now two versions of push forward. so if we suppose that there are f lower star alpha, where alpha is as before, is an isomorphism, right? But we can also, by that diagram, just write the composition, or write the f without the derived function, f lower star applied to the alpha. So it's an isomorphism. So then, well, we have a distinguished triangle, so we have f mapped to the G with the map alpha, complete this to a distinguished triangle, let's call the third object E. Right, so then we can apply to this distinguished triangle f lower star. Right, so if we know that this is an isomorphism, we can conclude that from this distinguished triangle, f lower star applied to the E is acyclic.
So why you say that here f lower star of alpha equal to f lower star of alpha?
Well, because we computing this kind of map in the d of x, right? Well, this is a fully faithful functor, right? So we can think about this as a map between two objects here, right?
Why f and g two objects here? Shouldn't we? What we prove? We're proving that RF lower star is conservative for quasi-coherent sheaves for DQ coax.
Well, in this case, these two functions are equivalents of categories, because we agreed that this is just an affine situation. S is affine, X is affine.
Okay.
Right, so that's an equivalent. If I have something home here, I can think about this as a home here, so I can, if I want, I can present this by the complexes with quasi-coherent terms. So I can call this now f and g as a complexes with quasi-coherent terms. So what I see that the f lower star of E is acyclic. Right? And f lower star on this category of quasi-coherent is exact. So f lower star is exact on Q core. Right? But it means that it commutes with the cohomology. So the cohomology, say hi of the f lower star of E, this is f lower star of the hi of the E. Right? So I know that this is 0 for any I. So I can claim, well, I know now that the push forward with the f of the hi is 0, but this means that the hi of E is 0. Right? Because, well, this is just a general property, very simple one, I would say. If you have a quasi-coherent sheaf, right, on this one, and the push forward is 0, then this sheaf is just 0.
Why is that true? The true for, I suppose, for affine.
Yeah, everything is affine, so it's kind of just a map between rings. It's something. I think it's maybe even easier, right? If you kind of have a map of the rings, if the complex is acyclic on one ring, if you continue on the other ring, it's also acyclic.
Yeah.
Or if module is 0 on one ring, it's 0 on the other.
Yes, it's just that module A module is 0, then A module as B module is also 0. It can be anything.
Yeah. So that's the end of the proof of the lemma. So we continue to do that 3 implies 1. Okay. Maybe I'll write this again. So 3 implies 1. This is what we're doing. Okay. So to show that base change map is an isomorphism, we work locally on S and S prime. So without loss of generality, we assume that S and S prime are affine. So then U and hence U prime is affine morphism and let me introduce notation. So let theta 0 be the map from the derived pullback of the push forward along U of the structure shift of S prime to the ordinary pullback. Okay, we always have such a map from the left derived functor to the functor. So now I want to formulate and prove two steps in this 3 implies 1. So in the first step, I want to prove the following claim. Theta, right, so which is the base change map, right? So I assume that, so 3 implies 1, I assume Torah dependence, and I want to show that the base change map is an isomorphism. So the map theta is an isomorphism.
Why we can assume that S prime is affine?
Well, because it's enough to show, by the definition of the Torah dependence, it's enough to show only for the kind of local neighborhoods of all points.
Yes, but the base change morphism uses push forwards, which are not local on S prime.
Yeah. Yeah, but this is not a problem. We want to check. We want to check that the theta is an isomorphism, right? Okay, and you have a map, and you can check that this is an isomorphism just by doing this locally.
Yes, because we don't use U lower star in the
So the step 1 is the claim that theta is an isomorphism if and only if, kind of similar to some computation that we've done before, the following RF lower star applied to the theta 0, then the product with E is an isomorphism. Kind of technical step. Right, so
Theta 0 is it's just the map from derived
from the derived functor to the
its
other function.
homologies.
No, to underived function. So that's the object.
To its zero homologies.
Yeah, if you can say it like this, yes.
And there is nothing apart from it because there is no homologies from the left.
No, this is the object, right?
Yes.
For this object, you kind of choose the K-flat resolution. You apply the F upper star to the K-flat resolution to the object. When you have a resolution, you get this. When you don't have a resolution, you get this. So that's just an application of this functor to the resolution. So let me write this K-flat. What's notation of K-flat resolution? Maybe L. That's a K-flat resolution for this thing, right? And then you apply F upper star to this morphism.
Yeah.
Okay, so I want to show that theta is an isomorphism if and only if this functor of the morphism, this morphism is an isomorphism. Okay, let's. Yeah, so since now U is affine morphism, and I have this lemma that I just proved that the R U lower star is conservative, I'm going to look at the R U lower star theta, right? So if I can show that this is an isomorphism, then theta is an isomorphism. So let's do this. This will be a map from the R U lower star. Now, now I just kind of do a tautological step. I just add the tensor product with the S prime, so the derived tensor product even, but over S prime, the thing doesn't do anything. And then I just write what I have on the kind of as a source of the map theta. So L U upper star R F lower star E. Right, so let me rewrite this by using the projection formula. So this will be R U lower star tensor product, so derived tensor product. Sorry, this is applied to the O S prime. Right, so then this will be the tensor product with the R F lower star E. Right? So this is what we get from the projection formula. So then another kind of way to simplify this in another projection formula. So this will be R F lower star applied to the following tensor product: L F upper star U lower star O S prime tensor product with the E. Okay. So that's now just another application of the derived projection formula. Okay. There's something. This wait. Well, yeah. So this is just an affine map. I don't need to derive it, so I can skip the R. Okay. So this is what was on the source of the map theta. Now, how about the target? So in the target, I have R U lower star, R F prime lower star, L U prime upper star applied to the E. So now I need to simplify this part. So this is isomorphic. Okay. Okay, so this is R F lower star applied to the R U prime lower star, and this is applied to the composition of the O X prime tensor product O X prime with the L U prime upper star E. Okay, so that's the formula, and I don't see immediately why that's the correct formula. So, well, first of all, of course, this doesn't that tensor product doesn't do anything.
We take RU lower star and RF lower star prime, combine into RG lower star, and then we RG lower star.
Yeah.
Just split in.
Yeah. So you kind of you take this. You still have the. Oh, I don't have a square. So this is kind of going in two maps in the square, and that's just another way to go by the another two maps in the square. Yeah, so that's the first step of the computation. Now I want to use the projection formula here inside. So this will be R F lower star. So this will be U prime lower star applied to the O X prime tensor product with the E. Right? So So that's the projection formula here. And again, since u prime is a base change of the u and u was affine, u prime is affine. Okay. So what was this thing? So now kind of the tautological rewriting. So R F lower star. So then here I can write this as the u prime lower star, F prime upper star of the O S prime, then the product with the u upper star O X, then the product with E. Right? That's the tautological way to write the same thing, right? Because I have u star lower, u lower star prime, right? But that's applied to the structure shift x prime. But these are just two pullbacks of the structure shifts. This is again structure shift, and that's the product of two structure shifts. So that's a tautological way to do this. Now, the next step, I'll keep the RF lower star, and then I do
Why is it in the product is underived here?
because I want to obtain as an argument of this function just the structure shift of the x prime, right?
Yes.
And this is just a structure shift OX prime, and this is a structure shift OX prime. So that does the product is again OX prime.
Yes.
And I can actually, if you want, I can write the derived as product, but it will be underived because the objects are just k-flat. Okay, so then the next step, well, we're almost done. There's kind of two steps left. So, and one step, and I don't want to prove, so I assume that you know this from algebra and geometry. So on this step, I just rewrite this formula as follows. So u lower star prime, f upper star prime, applied to the O S prime. So that's again application of the underived projection formula. Tensor product. Oh, this will be tensor product over x. Just a second. Yeah, the tensor product is the. This is what I claim, right? So that this is true. And this is the underived projection formula. Right? And that's since I get tensor product with the x, it doesn't do anything, so I can just keep this. And finally, the last step, I keep the R F lower star, and then they do underived base change. So that's the step that I assume you know from the algebraic geometry. But you can notice that well, the base change here that I do is underived. And so you can notice this also in a very special setting, right? You just apply this to the structure shift. You know a lot of the special properties that the map U is an affine map. So kind of very straightforward computation. So let's say this is star. So star is the underived base change. Maybe you actually. Sometimes this is done in algebraic geometry, sometimes it's not. But this underived version is something that you do in the algebraic geometry. So I want
Yeah,
to see
so it's not just underived version of just algebraic geometry. We need to know that f is flat, usually.
but in this case, I don't think that you need this. No. I think the condition that something is flat you need for the derived version. Oh, and again, you also need this because the only reason you write the assume that this is flat because you don't want to derive the second function. No, that I know that this is kind of not a good idea to leave this as an exercise, but I've done this exercise, it's not very hard, it works.
Okay.
Yeah, and also, since in this case, you don't need anything flat because you apply this to a flat object, to a K-flat object, so it's
that's
a very
true.
special case.
That's true.
Do we use tone dependence here
For this computation,
for this underwriting with change?
I don't remember. You might need this. Yeah, I think you need this. Yes, tone dependence. You need this. But you need to check this. Well, maybe you need tone dependence to a little bit more general statement. Maybe if you just have a structure sheet, well, check this. But probably you need this. Yeah. So that's the computation, and what's the upshot of this computation? So we see that if you just combine everything, the formula that we proved is that R u lower star applied to the theta is equal to the R f lower star applied to the theta 0 tensor product, derived tensor product with E. Right. I was computing this morphism, and I noticed that I can reduce this to this morphism. From this to this, right? Which is exactly the theta 0 tensor product with E. And hence this is the end of the proof of the step 1, right? Since we know that in this case U is RU lower star is conservative functor, so if we know that theta 0 is an isomorphism, then this is an isomorphism, and then the theta is an isomorphism. Okay. Okay, and the step 2, which is much easier and finishes the proof of this application. This is just a simple commutative algebra. So theta 0 is an isomorphism if and only if x, well, you can also kind of abuse notation a little bit. Instead of maps, you just talk about the schemes. So x and s prime are Tor independent. Tor independent over s. Right? But that's a very simple statement, because again, we can work locally. We can say that x is the spec of A and s is the spec of R. S prime is the spec of R. Right? So then if we try to understand this map theta 0, then this is precisely the A tensor product over R, so the derived tensor product with R prime, to the underived version of the same tensor product. Right, so that's the local computation commutative algebra. Right, so but this is an isomorphism precisely where there are no higher tors. So the condition that theta 0 is an isomorphism is clearly the same condition as the Tor independence if you do the computation locally. Right, and this finishes the proof that 3 implies 1. Right, so by Tor independence we get that theta 0 is an isomorphism. Then by step 1, we notice that if the theta 0 is an isomorphism, that theta is an isomorphism. That's what we want.
So isn't it proof that 1 applies to 3 also? Isn't it proof that 1 applies 3? So in both steps we have if
No,
and
but
only
we
if.
have these assumptions that we can work
Ah,
locally.
no, there's R f lower star theta 0 tensor E. If it's iso, it doesn't say that theta 0 is iso. So yeah, doesn't.
Yeah. So yeah, we do. What's left is to go from 2 to 3, right, to finish the proof. And that's just another page of computations, but we'll do this next time. Okay, so actually I'm out of time, yeah. So that's the end for today.